Ladies and gentlemen, welcome to our today's webinar, Why Software-Defined Vehicles Require Scalable Compute Platforms, in which we will get some key considerations in the design and evaluation of high-performance vehicle computers for SDVs. My name is Sabine Sinkule. I'm an editor at Hütig Medien, and I'm writing for the magazines Electronic Industry, Automobile Electronic, and E-Mobility Tech, as well as for our online magazine All Electronics.de. This webinar takes place in cooperation with ARM. A few words about our housekeeping. In the webinar, this webinar will be recorded and it will be later available for streaming in the webinar section on allelectronics.de.
Did we have a technical problem with our moderator?
I think we seem to have lost Sabine. Yeah.
Okay, I'll give a few seconds, and if the problem persists, we'll just start.
Yeah.
As an embedded software engineer before joining our ARM in 2010, where he has held several roles in strategy and product management. And the second speaker, John, he leads the automotive go-to-market team in the EMEAI region. And in addition to driving key ecosystem partnerships in EMEAI, his team is responsible for steering specific strategies in areas such as ADAS, the evolution of the vehicle EE architecture, and virtual prototyping. Prior to joining ARM in 2017, to lead market development activities in the area of machine learning, John held senior commercial roles in companies such as Canonical, Red Band, and Symbian. And with that, I will leave the stage to our speakers.
Thank you so much, Sophie. So I'm Guilherme. I think that bit of the presentation you probably missed. Together with John, we will be talking today about some important considerations that we hear when we're interacting with OEMs, tier ones, and different suppliers across the semiconductor industry. So I'll take you through the first half of the presentation and hand over to John later on. John, do you want to say a few words before we start?
No, just welcome everyone. Really pleased to be here. As Gil said, we hope you get a lot of value from this. We structured it in two halves, looking at some of the business considerations and then also some of the challenges, particularly with regard to addressing the needs of or meeting the needs of the software-defined vehicle challenge. So hopefully the audience will get a lot from that. Thank you.
Thank you, John. So without further ado, let's get started. First off, I will start with just one slide to talk about ARM and present where we are in the automotive supply chain. ARM is a 33-year-old company that specializes in designing CPUs, GPUs, ISPs, MCUs, intellectual property that gets licensed and then used in semiconductors. We operate across several industries, and some of you will be familiar with our presence in the mobile and consumer platforms. We also have a good presence in data center that has been growing recently. But we want to talk obviously about automotive today, and we have been for over 25 years in production in automotive through our partners, the semiconductor companies who design their own SoCs or microcontrollers using the central intelligence, central processing unit that we design. So we don't manufacture or design full semiconductors. What we do is design the architecture for central compute. And this is relevant because what we're going to talk about today are kind of high-level requirements that the impact of selection of compute platform has in enabling software-defined vehicles. On the left-hand side is a very busy chart with some product names that are used in different domains of the car. I'm not going to go into detail with that. The important thing is our IP is being used in by the top 15 automotive semiconductor companies in the world. They all have license for ARM technology. And currently, looking at the stats of shipments and productions, we are looking at over 50 ARM-based processors being installed into cars every second. So another 50 now have shipped. So based on that exposure to the industry, we wanted to share some insights, actually provoke some thoughts as well related to how the industry used to look at semiconductors in the past and the challenge that they are going to face as they transform themselves for a software-defined world. So before diving into the technology, it's important that we look at the opportunity, right? SDV is there because consumers expect a different type of user experience, a different type of relationship with the cars, with the purchases, the experiences that they had on different platforms, like this one, is reflected on what they expect of vehicles in the future too. To enable that, cars will probably have to become digital mobility platforms where services are delivered over the air for monetization post SOP. This, changes significantly how the business and the organization of the OEMs and tier one suppliers needs to reflect that. On this nice colorful chart here is a projection for Accenture on how automotive revenues are going to be augmented by software-enabled revenue in the future. Many analysts have different numbers. They all have very big numbers, and that's the important thing. This one is basically saying that, by 2040, this could represent about 40% of the automotive revenues. And the added services that could be delivered as software-enabled go from automated driving, so providing upgrades for the automated driving experience and package, digital mobility service, or enabling car features that could be just digitally enabled, could enable consumption of media as well in streaming services and things like that. So there's plenty of people looking at the opportunity. And where we want to take this conversation and what's needed in terms of compute to make that happen. So many of you will be familiar with the evolution of the architecture throughout the years. I didn't depict all the way to fully distributed ECUs on this chart, but you probably have been following the industry with the arrival of high-performance computer SoCs, that consolidation of functions have been growing and growing to the point where we are today, where next generation platforms are looking at using zonal controllers, aggregators around a more centralized, very powerful compute to deliver on user experience, to deliver on ADAS and automated driving. So the last two iterations that you see on the right, they are basically OEM options and not necessarily timeline evolutions, although some OEMs will probably follow that path. The important part is that we are identifying the two main domains that will enable or unlock that $1 trillion opportunity with software-defined vehicles. Now, things are much more complicated currently and than they used to be. It's not a case of buying black boxes with microcontrollers inside that could be defined by one metric or two. Um, Currently, just looking at where ADAS and automated driving requirements are going, and this chart depicts potentially one dimension, which would be the machine learning or AI compute requirements needed as you go from general safety regulation requirements to level 2, 3, and potentially 4, right? And this crosses 3 orders of magnitude. It's not insignificant. It's very challenging to design systems that are fully optimized in terms of cost and performance and power to cover all this spectrum. And this is a place where many OEMs are seeing themselves today as they plan ahead for the vehicles that will come out of the factories in 2028 or 2030. And the picture gets yet more complex as you overlay on top of the driving automation requirements, you overlay the user experience, the digital cockpit. And it's not uncommon to see large OEMs that go from very entry-level cars to luxury to have several configurations available, combining different levels of ADAS with different levels of user experience of digital cockpit. In this chart, just for fun, I created 11 dots that would represent not the full spectrum, but a few configurations that would be required to meet the performance to deliver different user experience levels and different automated driving automation features. Now, 11 configurations at a time where you would have, simpler microcontroller-based solutions coming from different vendors was one thing. As we look at the cost of developing semiconductors of this complexity and the software that goes on top of it, things change quite dramatically. And that's what we want to highlight. So some of the challenges along the road. For starters, we can't ignore that some of the performance requirements are not really set on stone today. They are uncertain for different reasons. Some of the workloads are just not mature enough. If you think about what level 4 driving is going to take, well, no one is really there today to say, let alone talk about how much optimized that could be for production. But you want to develop a platform that allows for innovation, allows the engineering teams to target that level in a few years' time. The other common problem is a little bit more basic. It's hard to compare apples with apples. The metrics that are being used commonly in the industry don't allow for high-level assessment of performance for the functions that these compute platforms are going to execute. For instance, if you're looking at a computer vision pipeline, you wanted to know potentially how many inferences per second you could be delivering within a power envelope. But that's not an easy comparison to be delivered. So typically, this is oversimplified with metrics like TOPS or DMIPS, which are probably inadequate to some of the use case. And the industry has a role here in getting together and coming up with different ways to solve the problem and allow that comparison to exist. So dimensioning of the platforms can be more correctly done. In the center is an interesting one, and it's not one that we tend to get involved very often, but the way the way accounting, the way organizations used to buy semiconductors used to be taking them as commodity, and looking at, semiconductors as wing mirrors or tires. And I think all products have differentiators and they're not simple. Um, but the level of complexity and investment in both hardware and software for centralized high performance compute is a completely other order of magnitude investment. So we're talking billions. And at this level, the unity of accounting cannot be only the unit cost of a silicon chip. It has to account for the opportunity unlocks. It has to account for the software development and validation costs for a given platform. And talking about development costs, that's a known quantity in the industry, that things are just getting more complex and more expensive. And those costs just make the whole program the center, the strategic center of OEMs that are targeting software-based products in the future. So next, what we're going to look at is just a few data points that I brought along to let us understand why it's difficult to imagine semiconductors for centralized compute in the same way that we used to do for simpler semiconductors. First is the massive increase in design costs. As the node process gets more advanced, you see jumps in the order of $200 million for potentially not a full linear scaling in terms of performance and power efficiency either, because some elements in the SoC just don't scale that well beyond a certain process level. That brings us to the middle part. We need to deliver more performance. And one way to do that is miniaturization and multiplication of different compute elements into the semiconductor itself. Now, an interesting quirk of the semiconductor production is that the smaller you get, the least yield you have. That means that you get more chips out of the factory that have defects on them and cannot be used. The solid lines on the chart, as you see, they go down from the left-hand side at 100%, which means 100% of the chips are good for use. And as the area of the semiconductor grows, the die size grows, the percentage of good chips that can be used goes down as well. Which means that if you look at the black one, which is the worst case scenario, that would be a model for a 3 nanometer process. And as you get to, say, 800 square millimeters, you're already looking at nearly only 20% yield. That means out of 5 chips you produce, 1 works. And that is just a massive cost that becomes very difficult to accommodate. On top of that, the industry across the board, beyond automotive, suffers from shortage of talent because there's a whole lot more demand for semiconductor designers. There is an ever-growing push for performance to be delivered, and then we start hitting that reticle size, which is the maximum size that you can get a silicon product, a die, for. Validation costs are incredibly expensive for silicon in this complexity, this size. And if something goes wrong and you have to do it again, then silicon spins can make or break a program. And on top of that, obviously, everyone wants to move fast. Everyone wants, accelerate time to market and innovation. So there's a lot of pressure on the hardware side of things. But on the software side of things, there is a learning curve of how this relates with the broader hardware platform that goes alongside software. Many companies have come out and create dedicated software units. There's a lot of investment. Mercedes-Benz is talking about having 25% of their R&D budget allocated to software by the mid of this decade. But the costs are massive, right? If you look at what McKinsey predicts ADAS and AD software development will cost the industry by 2030, that will be around $43 billion, okay? And on the left-hand side, also McKinsey projections on the relative cost of a hardware software development and validation costs. And the takeaway from here is that there is a massive software validation investment that needs to be protected. And the idea that, picking a different hardware platforms based on the unit cost or the cost optimized unit for a certain configuration doesn't scale, because in the end, the software costs will make it impossible to deliver a sustainable model. Just to have some fun, we created this example, which is probably not something that should be taken as the reality, but it illustrates a very important point. And the point here is that there are trade-offs on the hardware side that will impact your cost, time to market, risk of success on the software side. And if you can't deliver on software, then you're making a bad decision for the future. So in this case, we can look at a fictitious OEM 1 and a fictitious OEM 2, both ship about 5 million vehicles a year. Vehicle lifetime could be 10 or 15 years. We don't go that far on the model, so that doesn't really matter. And we assume a compute life cycle of 3 years. So the compute platform will be shipping in cars for 3 years. After 3 years, a new upgraded platform will replace that. Now, OEM 1 wants to optimize silicon cost and decides to go for something that requires them to slightly heterogeneous different compute platforms with different accelerators and so on and so forth. So they have one solution for the low end, one solution for the high end of their cars. And with that, they probably can, be more on the point for every configuration that they want, making sure that there's not a lot of software silicon cost wasted. OEM 2 takes a different approach. So they optimize the compute platform for software reuse and high portability. Now, we take some assumptions here. One thing that everyone hates to think is, pay more than they need for a chip. So OEM 1 did well and is doing just the best that is possible to get in terms of deal. And so additional cost is zero. OEM 2, because of the different approach, ends up paying about $50 additional per car for the 3 years that the compute platform is shipping. This translates into a hefty $6 million investment. If we think back to the SDV opportunity, then you will have the regular services that I guess either platform will deliver on. But those $50 that have been added potentially to the entry-level cars could be pushed to or designed to allow for specific services, upgrade services to be monetized through software-defined or software-based products. So we play around with the numbers here and just say, you know, your $8.99 Netflix subscription per month. If you get $8.99 out of 15% of the fleet for a total of 5 years after they left production, this already translates to something like $776 million, which is more than the investment that you put up front on the hardware side. Now, these are all made up numbers, right? The important concept here is to think about the rationalization of the platform for software reuse. And the next line down is a very important one too, because once you make the choice to maintain different platforms in productions, different compute platforms in productions, you have not only a huge initial cost of developing a separate stack, even if you're porting from the high end and cutting down features or the other way around, you have a huge initial cost, but you also have a maintenance cost that will hit you at every release. If we make an assumption that the first initial release is going to take an additional cost of, say, 60 million, which equates to about less than 300 engineer years, plus 5 million per release, with quarterly releases over the 5 years, that could already translate something in the order of $150 million for that platform alone. And this doesn't even account for the risks of developing and maintaining two different software stacks and the risk of delaying start of production, which you have seen the news has happened with more than one OEM recently. So in this very non-representative example, you already see a difference where a additional upfront investment on the hardware side and a simplification of the compute platform would require an upfront investment, but it still be something in the order of 331 million, better off than the option to well, nickel and dime on the compute platform that OEM on. So I'll leave that thought with you. And finally, obviously, we want to show what's the vision, right? What would be the ideal case? The ideal case is obviously that you have as little additional cost as possible to target your single software platform onto all the different hardware configurations that we have. And the message will be that because of costs, these hardware configurations will have to be rationalized too. And you know, having fewer platforms might actually pay off in the long end. So these are some of the challenges, and no one can go it alone. So I'll hand over to Joe now to talk about some of the initiatives across the industry that will help us be more efficiency and get to the SDV future.
Thank you, Gil. Really appreciate it. Really for part of the session, I think. And as Gil said, you know, we're definitely on this journey together, and it's a journey of digital transformation for the entire automotive industry. When we look at what's required for that digital transformation towards a world of the software-defined vehicle. We look at having safety, security, real time as table stakes, and having those in place, then we can approach the software complexity challenge by breaking it down to 4 pillars that we believe are foundational to the industry's success. First, we have standards. The focus on value for the industry is really enabled by foundational non-differentiating software that enables maximum reuse and reduces fragmentation and reduces cost. New software methodologies like CI/CD, mixed critical orchestrators, advanced AI algorithms enable us to be far more agile in our delivery of software. Vehicle simulation in order to scale validation and testing of software, and access to vehicle simulation models in the cloud are really critical for software developers up and down the entire stack. And industry collaboration. No one company can do it all, and we really do have to come together as an industry to be able to realize this. And that's why at Arm we're really proud to be one of the founding members and the main sponsor of Sophie. So Sophie is a scalable open architecture for embedded edge. It's an industry-driven initiative focused on developing standards-based software framework for automotive. We celebrated Sophie's second birthday in September, and we're really excited that the community has grown now to over 100 members. The focus will remain on developing open source framework and reference solutions to solve key technical challenges like mixed criticality and virtual software development infrastructure. And going forward, the teams from all of these organizations will also enable use case specific reference solution blueprints, expand our community-driven integration labs, and continue to build more strong cross-consortium partnerships. So we're really excited. We're really excited by the progress that we're seeing, from the industry in terms of coming together around initiatives like Sophie. But let's drill down into Sophie in a bit more detail, and what it delivers. So we build on foundational software. We've spoken about that already, and Arm System Ready is an example of that. It provides some low-level primitives that ensure that you can boot a Linux distribution, a range of Linux distributions out of the box across a range of different ARM-based SoCs. That's a fundamental foundational software and part of the standards that we've already spoken about. We also have the opportunity now that ARM CPUs are being deployed in cloud infrastructure by cloud service providers. We now have a situation where we have the same instruction set architecture in the cloud as we have in the vehicles. We have this environmental parity between the cloud and the edge, the cloud and the vehicle, which allows us then to kind of look at some of those new software methodologies and understand, right, how can we really leverage those to the benefit of the industry. So we're looking at cloud native methodologies like orchestration, like virtualization, and containers. And looking at how we kind of extend the standards around those methodologies to make them fit towards more automotive appropriate solutions. So extending those standards to work in mixed criticality systems where you have real time and safety as really hard requirements. So that's the one of the fundamental focuses of Sophie is to be able to enable the automotive industry to leverage those software methodologies that we see in the cloud, make them appropriate for the automotive industry, and make the industry more efficient, more productive. And so how would we see that manifest itself? We would expect to see it in a more efficient automotive development. If you look at a traditional automotive project, you have kind of a serialized set of milestones in the project, from SoC design and low-level software development in the early stage, moving then on to ECU design, software development, and then finally into the application development and system integration phase. By leveraging those cloud-native methodologies, by decoupling the hardware and software, we can parallelize some of that timeline. So the objective here is to have software development decoupled from hardware, and enabling that to start earlier in the project when SoC design and ECU design are still taking place. And then the goal there is obviously to shift left the target production dates of the vehicle, to shorten that development time cycle, but also then to be able to continually delight end customers through a life cycle of OTA updates and feature upgrades during the lifetime of that vehicle in the market as well. A really, really great example that we've seen of this recently, which touches on all of the 4 pillars that we've talked about, was a recent announcement from Continental and AWS. The QR code in the top corner will take you through to their press release, so you'll be able to read about it in more detail. But essentially, Continental took their ARM-based CAD platform, ECU platform, and virtualized that, and leveraged Electrobit's AutoZar software implementation in that virtual ECU environment, and have that running on ARM-based Graviton instances in the AWS cloud. So we got virtual ARM-based ECUs running on ARM-based CPU cloud instances. And the objective and the expected benefits that Continental and AWS expect from this is a shortening of development cycle by up to 12 months. So this is a perfect example of those 4 pillars, where leveraging standards that have already been deployed, leveraging new software methodologies, enables vehicle simulation, and through industry collaboration, really pulling in those timescales. We see every single one of those pillars that we spoke about earlier coming into play to deliver this solution. And from an ARM perspective, that's exactly what we're doing here as well, delivering solutions, both leveraging the rich portfolio of ARM IP that's available, but we're also bringing those together, aiming to accelerate time to market with reference compute subsystem deliverables that are coming from ARM, but also interleaving those with rich solution software and SoC design execution solutions that come from the ecosystem around ARM too. We can see these examples of SoCs from our partners delivering across the entire range of needs in the vehicle, from zonal controllers and digital gateway solutions, all the way through to really rich digital cockpit experiences and IVI platforms, all the way through to advanced driver assistance systems as well. And not only are our traditional silicon partners delivering a huge range of automotive solutions to the market, we're also engaged with a number of automotive OEMs that are designing their own custom high-performance compute solutions as well. So we've got multiple OEMs in production development stage, and in combination with our silicon partners, millions of deployed vehicles on the road leveraging leveraging these ARM technologies. So that really kind of wraps up the session for today. In summary, looking back at the material that Gil shared, we hope that you take away from this that the vehicle compute platform really must be a long-term strategic choice. Hardware and software costs must be considered together and not separately, and also across generations of vehicle platforms as well. Investment's absolutely essential to unlock monetization throughout the life cycle of that vehicle, continue to delight customers through delivery of features after the vehicle has been delivered into the market. And central compute scalability is challenging, but it can be achieved efficiently and with balance and with keeping software in the balance too. And then to realize the SDV growth opportunity, it really takes a village. It takes more than a village. It takes the whole industry. Modern automotive software really depends on mature cross-industry ecosystem to function, and we see that realized across the whole ARM ecosystem every day. Deeply embedded development methodologies really will struggle to scale to central computers, and so we have to look at leveraging some of the new software methodologies that we see prevalent in the cloud and looking at how we extend those so that we can take advantage of those in the automotive space. And then finally, standards and collaboration are really key to sustainability of the SDV economic model. It's very difficult for one organization to do it all on their own. So that brings things to a close in terms of the presentations. One last thing I would like to say is ARM is hosting an automotive partner summit in Cambridge on the 26th of October. It's both an in-person and virtual event. If anyone's interested in attending, you can reach out to either Gil or myself, and we can get you enrolled on that program. So with that, that's all our material covered, and we'd like to open the floor to any questions that we've received.
Okay, thanks, Gil. Thanks, John. And now to the question and answer. As I already said, you can write your questions in the chat. And we have one question, which is, what are the main drivers that automotive OEMs have decided to invest in customized semiconductors?
Can take this one, John.
Yeah, would you like to?
Yeah. So it is a very good question, and there are many drivers for that. I think the most important thing to observe is that there is no one-size-fits-all solution. So OEMs will take different routes for different problems. They will have plenty of options in the ecosystem for commercial off-the-shelf silicons today to take them in certain cases to where they are. But what we see is a little bit of a trend in automotive OEMs taking that as a more strategic long-term decision to control the cost and the technology and the ability to differentiate in their markets. So that's what I see as the main drivers for OEMs going into custom SoCs.
Okay, thank you. Another question is, Sophie gathered great momentum, adding over 100 members in a short period of time. What value does it bring to the industry compared to other consortia, such as Eclipse, SDV, Covisa, or AutoStar?
Okay, shall I take that one? Okay. Yeah. So it's a great question. There are a number of different consortia initiatives in the automotive space. Sophie's working very closely with all of them, actually. In actual fact, last week in Cambridge, we had the Automotive Vehicle Compute Consortium here at the ARM offices, and we had a panel discussion with AVCC, with Sophie, with Covisa, with AutoWare Foundation, all on the same panel discussion. And I think the general consensus there is that there's there's a huge amount of work to be done to realize the vision of the software-defined vehicle. Sophie has a specific area and remit that it's looking to add value in, and that's how do we extend those cloud-native software methodologies to the automotive space and make them really relevant in a world where you have to deliver safety and real-time mixed criticality systems. So Sophie has a really focused effort on delivering that piece, and it complements the efforts in Eclipse SDV, which has a much broader focus than just that. So there's a lot of opportunity for all these consortiums to work together and make sure that we're all focused on the relevant piece of the industry challenge that each of those consortiums can add value.
Okay, thank you very much. That brings us to the end of today's webinar. As I already said, you can stream this webinar pretty soon on allelectronics.de. And yeah, have a good day and goodbye.
Thanks,
everyone. Bye.
Bye, everyone. Bye.